Okay, this problem is right out of your book towards the end of chapter 6. And the scenario is an experiment that's set up to measure the tension pulling a cart. And so let's take a look at this FBD down here. So imagine you had a cart, fairly low friction on a level surface, and that there is a constant tension pulling the cart to the right. But there's also some friction opposing the motion. And so the data that we have is, as a function of time, we have the scenario where the cart is given, first of all, some initial velocity in the x direction without the tension acting on it. So there's only the frictional force opposing the motion. And that would be this first two columns here. So this would be the velocity as a function of time. The initial velocity is 1.2 meters per second, and then because the acceleration is any parallel to the x naught, because the x net force is any parallel to the x naught, and the acceleration will also be in that direction. The speed, rightward speed decreases. So we have that every quarter of a second, we have that data. But we also have data for when the tension is applied to the cart and both forces are acting. And in this case, it starts at 0. Okay, so the first thing we do, that I did, is I took this data and I had Mathematica tell me what the best foot straight line was for the first two columns. That gave me a minus 0.124 meters per second, straight line linear regression fit. And then for the first and the third column, since the rightward velocity is increasing, that corresponds to a positive slope and a positive acceleration, 1.55 meter per second. And so that I show down here, if I can get to it here. Let me see. I can just scroll you down and show you what I did in Mathematica. So here's what I did in Mathematica. I took the data from that table and I put it into well, curly bracket form, and you can see here's the first row, first column, second row, first column, second column for this scenario where it starts with an initial velocity of 1.2 meters per second. That's what this is, and then slows down. And the second data set is the what happens when there's a speed up scenario and the tension is acting. And so I then asked Mathematica to tell me what the acceleration for the roll velocity and for the pull velocity were. That's what these two data sets were. And so it came back. This is how you do that, incidentally. And it told me that the first data set is modeled with this. And this multiplier for the x is going to be the acceleration. That's where the 0.124 came from. Second data set is modeled pretty well with this. And again, the coefficient, the constant multiplying x is the slope, and that's therefore the acceleration, 1.55. Okay, so from the data, the short story is, from this data with some help from Mathematica, I got the best fit accelerations for both of these. Now, from the free body diagram for each one and the Newton number 2, I can figure out from the first data set, I could figure out what F sub k is with a force analysis. And then knowing what F sub k is, I can then figure out what T is when I go to the second thing. Again, doing a force analysis. So starting with this one then, the first one, where only F sub k is acting, there's no tension pulling it. The x component, number 2, is minus F sub k equals the m times a sub x, and in the y component, n is equal to mg. And so that would mean, since this is going to be some mu sub k times n, that minus mu sub k times mg is equal to m times a sub x, and m is therefore equal to minus mu sub k times g. So let's progress to the second one. If I know what mu sub k is, then I know what a sub g is. And I do in fact know what mu sub k is. I can figure it out because I know what a sub x is from over here. Putting that on the back burner temporarily, let's go and look at the second one. Okay, the second force analysis, the Newton number 2 in the x direction is minus f sub k plus t is equal to m times a sub x. This is a different a sub x from the above one. And in the y direction, n equals mg. And so we're going to conclude then that minus mu sub k mg plus t is equal to m times a sub x. In other words, t is equal to ma sub x plus mu sub k times mg. It's m times a sub x plus mu sub k times g. And so we know from 1 that mu sub k is the ratio of 0.124 meters per second over 9.8. There should be another negative in here. So this, to make this come out positive, there should be another negative inside here because the acceleration is negative. So that allows me to put in a value for this, and the a sub x is what we got here, 1.55. And so the tension now can be computed as the mass of the cart, which is 1/4 of a kg, it's given in the problem, times the quantity of 1.55 meters per second plus the previously calculated mu sub k of 0.013 times the acceleration of gravity, and that turns out to be 0.42 newtons. Pretty cool.